Hey Chem students, welcome back to Bridging. This is the final one of the lectures that I'll be taking. After this one, you're going to hear from Chris Austin, and he is our lecturer that's based out of Sydney. So I'm going to talk to you a little bit about electron configurations and periodic trends. So if you remember from the last one that you listened to, we spoke about atoms and how atoms are these particles that are made up of subparticles, including neutrons, protons, and electrons. And the neutrons and the protons are both in the nucleus, and they have most of the weight, but then there's this cloud around the outside of them called electrons. And the number of electrons and protons is what determines what type of an element the atom is. So in terms of electrons, they're really tiny, tiny, tiny particles, and they have a negative charge. Electrons and the nucleus are held together by something called an electrostatic attraction. It's basically because the electrons have this negative charge, the nucleus, because of the protons in it, have this positive charge, so the electrons are held in place by this positive versus negative charge that pulls them in. Each electron has a specific amount of energy, and the electrons of similar energy are grouped in energy levels called shells. So remember I said that it's the electrons hang around in a sort of cloud. It is a cloud, but it is structured. So we talk about it in terms of different shells. And what this means is that at the bottom level of our bookcase, or the bottom shell number, has the lowest amount of energy electrons. The highest shelf, or the highest shell, has the highest amount of energy. Now, one of the reasons for this is if this is closer to the positive charge of the nucleus, then it doesn't take as much energy to hold it there. Whereas if you move further out, then you've got to take more energy to hold it in place. So in terms of the energy levels, what we talk about is that they have a maximum number of electrons in them. So you can only hold so many electrons in these shells. So in the first one, you can actually only hold 2 electrons. If there's any more than 2 electrons, then they have to bump up into the next shell. And then we know that they'll increase in terms of this little formula. They're equal to 2n2. So if n is the first shell, n energy level number 1, then that means that we're going to have 2 times 1 squared, which is equal to 2. 2 is the maximum number of electrons that we can have in the first energy level. You can see with the second energy level, we've got 2 times 2 squared, which is equal to 8. So we can have 8 electrons in the second energy level, or the second shell. And you can see that this increases as we go up in energy level. Now, one thing that we should note is they don't actually fill in that order, and this is something that sometimes confuses students. What will happen is you'll fill shell 1 first, then you fill shell 2 next, then shell 3, but it will only fit 8 in there before it bumps into shell 4, and then it will come back into shell 3. We're going to do a lot of practice doing this filling of shells once we start the chemistry course proper. So this is more to get you used to the idea that the shells exist. I'm not going to be asking you in this lecture to actually start separating electrons out into shells. So in terms of what this tells you though, we already know that in terms of the periodic table, we have periods and we have groups. The cool thing about the periodic table is that it's separated out in terms of the electron shells. So period 1, which is that top row, that has all of the atoms in that scenario are only using the first energy level. If you go down to period 2, then we're looking at using the second energy level. And this continues down as we continue down the different periods within the periodic table, until we get to the point where we're beyond the elements from 20 onwards, and then what will happen is that we start splitting them up between different energy levels, depending on the number of electrons. We also know that along with the periods that will tell us what the energy level that there is using, we know that if we go down the groups can tell us also what is happening in terms of where the electrons are sitting. So, in hydrogen, we know that there is only one electron and it's in the first shell. When you drop down to lithium, we've got 3 and there is 1 in the second shell. With sodium, we know that there is only 1 in the third shell. And potassium, we know there is only 1 in the fourth shell. This lonely electron that is in the outermost shell is what we call our valence electrons. So the last electron in any shell, the last one where we have just 1 electron floating out there on its own, that is called our valence electron. Now group 2 elements will contain 2 electrons in their outermost shell. So our group 1, which is that first row on the periodic table, they'll have 1 valence electron. When we look at the second group, we know that there are 2 electrons in the outermost shell. And when you go to the third group, you'll find that there are 3 in the outside. Now this valence electron is the number of electrons in the outermost shell. And valence electrons are what determine the chemical properties of an atom. All of the elements in groups 1A through 8A, so this doesn't include the transition metals, have the same number of electrons in their outermost shell. So the group number is equal to the number of electrons in their outermost shell. Group 1 has 1 electron in its outermost shell. Group 2 has 2 electrons in its outermost shell. Group 3 has 3 electrons in its outermost shell. And along the period, so this is going down the columns of the periodic table, along the period, which is the row, the number of electrons in the outermost shell increases. The elements in one period have different chemical and physical properties. So what we mean, hopefully this can put it all together for you. Group 1 is down here. And what we automatically know, because they're in group 1, is that all of these only have 1 electron in their outermost shell. This one is group 2. And these all have 2 electrons in their outermost shell. Let's skip the transition metals for a bit and we'll look at this one over here, which is our group 3. We'll find that they all have 3 electrons in their outermost shell. These will all have 4 electrons in their outermost shell. The next one all have 5 electrons in their outermost shell, until we go all the way up to our noble gases, which have 8 electrons in their outermost shell, which means their outermost shell is full. So remember we were saying that if something's in a group, it has similar chemical properties. The reason for that is because of the number of valence electrons. Now what we've just said is that you'll find as you go across a period, it's using the same shell number. So if we look at this one here, this first period, these ones, they have only used the first electron shell, the first energy level. These ones here have used the second energy level, the third energy level. And what we find here, so for the second energy level, we know this one is in group 1, it's in period 2, so it is using the first energy level, so second energy level, and it has 1 electron in its second energy level as its valence. This one will have 2 electrons in its second energy level. We drop down to here, and we've got onto the third energy level, but we know with sodium, we only have 1 electron in the third energy level. A way that we can draw electrons, because what is most important about an element and what gives it its chemical properties is actually the number of valence electrons. So the way that we can draw them is using something called this dot diagram. It's also called a Lewis structure. And what it is it is the symbol for that element and the valence electrons are placed around it. So if we look at aluminium, for example, if I jump up back to the periodic table and I try and find aluminium, it's over here. It has an atomic number of 13. So this means that it has 13 protons. It will also then have 13 electrons. I know that it is in period 3, so that means it has 3 energy shells. And I know that it is in group 3, so that means that in its last energy shell there are 3 electrons. So I can write that out. 2 in the first one, 8 in the next one, 3 in the last one. So I have 3 valence electrons, and the way they're drawn in this image is just with dots. 1, 2, 3. This is a really good table, just so that you can see the dot diagrams just for the first few of the elements. And you can see how we draw their dots. And what you can see with these ones over here, which are our noble gases, is that they're all full, because they will only ever have 8 in the outer shell. Now, there's a couple of other patterns that I want to bring your attention to with the periodic table. It's actually a nifty tool. It tells you a lot. One thing that the periodic table will tell you is about the atomic size. Now, the atomic size is based on the radius of the atom. And what you can see is that the atomic radius increases down a group. It increases down a group because we're getting more and more electrons and they're moving out into the next shell. The atomic radius actually decreases across a period though. So even though we're getting more electrons, we're not changing the shell size. We're not changing the number of shells. So if we look here, we're in period 2, which means we're in shell 2, and we see that we get smaller as we go across because the number of protons is increasing just as the number of electrons is, which means the positive charge is increasing. So it can pull the electrons closer into the nucleus. So we go across, we get a decrease, but if we go down, we get an increase. In terms of ionization energy, this is the amount of energy required to pull an electron from the outermost shell. So we know that if these ones here are going to be really tightly held together because they have a large number of protons, it's going to be a lot harder to pull that electron out, which means the ionization energy increases as we go across a period. The ionization energy decreases down because we're increasing the radius, which means the electrons are now going to be further away from that positive charge of the nucleus, so it's going to be easier to pull them apart. We also know that metallic character can be distinguished based on where something is placed on the periodic table. Now, metallic character is if an element can lose an electron easily. The more metallic elements are right down this corner, and the least metallic elements are up here in this corner. So metallic character decreases across a period and it increases down a group. So just a summary of the trends of the periodic table, this is a really helpful diagram to have and something that you can use. Again, we're going to go into this in a lot more detail in the chemistry course proper. So this is just a taster. So please make sure that you're familiar with this information before you jump into classes next week and the week after. Good luck, and I will see you when we start the course proper.